From the moment consciousness emerges each morning until sleep returns each evening, humans operate under fundamental assumptions about existence. The earth feels solid underfoot, the heavens stretch infinitely overhead, and time progresses in an unbroken chain from past to future. Yet contemporary physics presents findings that fundamentally challenge these seemingly obvious truths about reality. Recent developments in quantum mechanics reveal phenomena suggesting that what we perceive as stable, concrete reality may be far more mysterious than previously imagined. Some researchers now propose that the universe itself might be illusory, a complex deception masquerading as substantial existence. These discoveries compel us to examine whether our universe actually exists in any meaningful sense. In 1935, Albert Einstein collaborated with Boris Podolsky and Nathan Rosen to formulate a thought experiment that questioned quantum mechanics' most puzzling implications. Their proposal, known as the EPR paradox, focused on whether the universe operates according to locality, the principle that objects only influence their immediate surroundings, or whether more mysterious connections exist. Our daily experience suggests locality governs everything. Moving a chair requires direct physical contact. Distant objects cannot affect each other without some connecting medium like rope or wire. This intuitive understanding aligns with how we perceive spatial relationships and cause and effect mechanisms. However, the EPR paradox highlighted quantum entanglement, a phenomenon where particles that once interacted remain mysteriously connected regardless of separation distance. If you measure one particle's properties, its entangled partner instantly responds, even across cosmic distances. This appeared to suggest information could travel faster than light speed, violating relativity principles Einstein himself had established. Einstein found this concept deeply troubling, famously dismissing it as spooky action at a distance. The EPR team believed quantum mechanics must be incomplete, hypothesizing that hidden variables, unknown factors, could explain entangled particles' seemingly impossible behavior. If scientists could identify these hidden variables, they argued, the mystery would dissolve and the universe would again conform to local interactions. Yet quantum mechanics offered no such comfort. According to the theory, entangled particles genuinely exhibit non-local behavior, with one particle instantaneously affecting its partner regardless of distance. No obvious mechanism explains this through hidden variables or local effects, creating a profound scientific division. Some physicists, following Einstein, insisted quantum mechanics was fundamentally incomplete. Others accepted that the universe might operate far more strangely than classical physics suggested, with non-local connections playing essential roles in reality's fabric. This debate remained unresolved for decades, but sparked intensive interest and investigation. It forced physicists to question their field's fundamental assumptions and consider whether reality might be far less straightforward than previously believed. This intellectual shift proved crucial for modern physics development, paving the way for new theories and experiments that would further challenge classical universe models. Physicist John Bell's work in the 1960s built upon the EPR paradox to create Bell's theorem, which provided frameworks for actual experiments rather than hypothetical scenarios. Bell's inequalities could determine whether the universe truly operated locally, as Einstein hoped, or according to quantum mechanics' strange non-local principles. These experiments demonstrated that no local hidden variables could explain entangled particle behavior. Results confirmed that the universe does not operate strictly locally. For Einstein, who died in 1955, this would have been disappointing, he had hoped. Deeper physics understanding would restore predictable local universe concepts. Bell's theorem and subsequent experiments transformed the EPR paradox from a quantum mechanics challenge into key supporting evidence. The universe appeared fundamentally interconnected in ways classical physics could never explain. Questioning existence's foundation. Human perception of the universe relies entirely on sensory experience. We trust that observed, heard, and felt phenomena represent genuine reality. Trees feel solid when touched, skies appear blue to vision, and gravity consistently pulls objects earthward. These experiences create an apparently stable, predictable world. But what if reality lacks the concrete nature it seems to possess? What if our experienced world represents merely a mirage, shaped entirely by mental processes? Philosophers have questioned reality's nature for millennia. Ancient debates centered on whether the world exists independently of human perception, or whether experience entirely shapes it. Plato imagined that our visible world represented only shadows cast by deeper, truer reality. Other thinkers suggested everything we know might be mental constructs, projections that appear stable only because psychological necessity demands it. Modern science has added new dimensions to these ancient philosophical questions. Quantum mechanics, particularly, has disrupted many classical assumptions about universal nature. In the microscopic realm, phenomena don't behave as expected. Particles can exist in multiple locations simultaneously. Objects can affect each other instantaneously across vast distances, and some things appear to exist only when observed. This strange behavior has raised serious questions about reality's fundamental nature. Our everyday experience suggests the universe follows clear principles. Dropped glasses shatter, room traversal moves you from one location to another. But quantum mechanics reveals these rules may not apply at the most basic levels. Particles comprising everything around us behave in ways completely foreign to normal understanding. They lack definite locations until observed, a phenomenon called superposition. Before measurement, particles exist in probability clouds where they can occupy multiple states simultaneously. Only upon observation do they choose a specific state. If the universe only takes definite form when observed, can we still claim it exists independently of observers? Is reality something external, fixed, and stable? Or is it fluid and constantly changing based on our interactions with it? These questions also concern the observer's role. Quantum mechanics suggests observers play crucial roles in shaping the universe. Schrödinger's famous thought experiment illustrates this concept. A cat placed in a box with a 50 to 50 chance death device remains both alive and dead until someone opens the box to observe it. The cat's fate only becomes real when an observer looks inside. This thought experiment demonstrates quantum mechanics' strange and counterintuitive nature, while suggesting reality might depend on observation itself. Such thinking aligns with certain philosophical traditions, particularly Eastern philosophy. Buddhism's concept of Maya refers to the world's illusory nature, suggesting perceived reality is not ultimate truth, but rather a veil hiding deeper, more fundamental truths. Similarly, modern physics might be revealing that our experienced universe represents a kind of veil, masking a more complex, less intuitive underlying reality. Quantum entanglement provides one of the most striking examples of how quantum mechanics challenges reality understanding. When particles become entangled, they remain connected regardless of separation distance. Changing one particle's state instantly affects the other, even across universal distances. This seems to defy space and time understanding, suggesting distance and separation might be illusions at fundamental levels. Bell's theorem, shattering classical reality assumptions. Bell's theorem transformed the puzzling implications of the EPR paradox into testable propositions. Before Bell, quantum mechanics debates remained largely theoretical. The EPR paradox raised serious questions about universal governance by local interactions, but no clear testing method existed. Bell changed this by demonstrating how to determine whether quantum mechanics' strange world truly defied classical locality ideas. Bell's theorem represented a groundbreaking advance because it didn't merely ask whether hidden variables might exist. It outlined mathematical inequalities, Bell inequalities, that could test whether these variables could preserve locality principles. If quantum mechanics was correct, experiments would violate Bell inequalities. If Einstein was right, the inequalities would hold, indicating hidden variables must explain the results. Scientists began conducting these experiments in the 1970s and 1980s. The first major Bell inequality test occurred in 1972, led by physicists John Clauser and Stuart Friedman. Their work was groundbreaking as the first genuine attempt to measure whether entangled particles truly behaved in ways unexplainable by local hidden variables. Another important breakthrough came in 1982, with Alain Aspect and his team's experiment in France. Results were clear. Bell inequalities were violated, meaning no local hidden variables could explain entangled particle behavior. Particles separated by great distances could influence each other instantaneously, as if space and time didn't apply at quantum levels. Bell's theorem demonstrated that quantum entanglement wasn't merely an odd theoretical quirk. It was a fundamental aspect of universal operation. Entangled particle behavior couldn't be explained through any classical means. Confirming quantum mechanics was pointing to reality that defied everyday experience. One of Bell's theorem's most exciting consequences is how it opens new technological possibilities. Quantum entanglement, once considered a strange curiosity, has become key research areas for developing technologies like quantum computing and quantum cryptography. In quantum computing, entangled particles can process information in ways classical computers cannot match. The instantaneous connection between entangled particles can solve complex problems far faster than traditional methods allow. Similarly, quantum cryptography uses entanglement's strange properties to offer new communication security methods. Any attempt to eavesdrop on entangled systems would immediately disturb the particles, alerting intended recipients to breaches. Because entangled particles can share information instantly, this suggests information might not be tied to physical objects as we typically think. Some physicists speculate that information might be a fundamental universe-building block, more basic than matter or energy. Understanding quantum entanglement's implications. Quantum entanglement has emerged as one of modern physics' most puzzling and fascinating aspects. To grasp entanglement's significance, we must consider what it reveals about reality. In classical physics, events are separated by time and space, with cause and effect relationships following clear rules. Throwing a stone into a pond creates ripples spreading outward from the entry point. You can trace back the effect, ripples, to a specific cause, the stone. There's a clear connection between cause and effect, bound by space-time laws. Quantum entanglement throws this clear connection into question. Imagine two entangled particles, one on Earth, the other on the galaxy's opposite side. Measuring the Earth particle's state instantly causes the distant particle's state to adjust to match the measurement outcome, despite no time for information travel between them. This instant connection doesn't follow space-time rules governing the classical world. Instead, it suggests particles are linked more fundamentally, as if they're part of the same system regardless of distance. Entanglement first challenges causality understanding. In the classical world, causes lead to effects in logical sequences, but quantum entangled particles don't seem to follow this sequence. One particle's measurement outcome immediately influences the other's state without any apparent cause and effect relationship. This raises possibilities that the universe at its most fundamental level may not operate according to strict cause and effect rules we observe daily. Some physicists suggest entanglement points to reality, where time and space aren't as fixed or fundamental as once thought. In this view, entangled particles aren't communicating faster than light. Instead, distance concepts between them are meaningless. Particles are part of the same system, and their separation is an illusion created by limited space-time understanding. From this perspective, quantum entanglement might reveal that boundaries we perceive between objects, events, and even time itself aren't as real as they seem. This idea can be difficult to grasp because it challenges so much we take for granted about our world. A universe where objects appear separate and distinct. A tree differs from a rock, and someone on the planet's other side isn't directly connected to you. But quantum entanglement suggests this separateness might be an illusion at deeper reality levels. If particles can remain connected across vast distances, perhaps the universe is more interconnected than we realize, with unseen links beyond usual space understanding. Another way to consider this: reality might not consist of individual objects at all, but rather of relationships. Classical physics conceptualizes the universe as independent object collections, each with properties moving through space and time. But in the quantum world, these objects can't be fully understood in isolation. Their properties only make sense in relation to other objects, particularly when entangled. This suggests reality's fundamental building blocks might not be things, but relationships between things. We tend to think of ourselves as distinct individuals, separate from surrounding worlds. But if everything is fundamentally interconnected, boundaries between self and other might not be as clear as we think. This has led philosophers to suggest quantum entanglement could provide new ways of thinking about consciousness and existence. If particles are connected across space, could consciousness itself be part of this interconnected fabric? Entanglement's most puzzling aspects relate to information. It has led physicists to wonder whether information itself might be reality's most fundamental building block, rather than matter or energy. Some theories suggest the universe might be built not from physical objects, but from information, with entanglement being one way this information is shared across the universe. If true, this would further blur lines between reality's physical and non-physical aspects. Information, unlike physical objects, isn't bound by the same space-time rules. It can exist in many forms, and entanglement might glimpse how information operates at the universe's most fundamental level. Entanglement also questions the observer's role in shaping reality. In classical physics, object properties exist independently of observation. But quantum mechanics suggests observation plays crucial roles in determining entangled particle states. Before measurement, particles exist in superposition where properties aren't fixed. Only after particle interaction do properties collapse into definite states. Beyond Einstein, how quantum mechanics defies spacetime. Quantum mechanics and Einstein's relativity theory, particularly general relativity, represent two pillars of modern physics, but they describe the universe in vastly different ways. Einstein's theory presents smooth, continuous space-time fabric that governs massive objects like stars and planets. In this view, space-time bends around objects with mass, and this bending creates what we perceive as gravity. Relativity succeeds incredibly at explaining universal, large-scale structure, from planetary orbits to galactic motion. But quantum mechanics, dealing with the universe's tiniest particles, tells a completely different story, one that challenges space-time understanding itself. Key differences between these theories lie in space-time treatment. In Einstein's theory, space-time is continuous fabric, meaning it can stretch and warp but has no gaps or breaks. Objects move smoothly through space-time, and time passage is affected by factors like speed and gravity. For example, time moves more slowly for someone traveling near light speed or standing near massive objects like black holes. This is time dilation, a key relativity prediction confirmed by many experiments. But quantum mechanics paints very different pictures. In the quantum world, space and time don't behave smoothly and continuously, as relativity suggests. Instead, at the smallest scales, space and time seem to break down into discrete, almost pixelated units. In this strange world, particles can pop in and out of existence and don't move in smooth paths through space. Instead, they jump from one location to another in quantum tunneling. This behavior completely contradicts spacetime's smooth, predictable nature in general relativity. One of modern physics' biggest challenges is reconciling these two universe pictures. One famous example of this tension is the black hole problem. According to general relativity, black holes are space regions where gravitational pull is so strong that not even light can escape. At black hole centers are points called singularities, where space-time is thought to break down entirely. But quantum mechanics tells us this picture can't be complete. In the quantum world, information can't be destroyed. But general relativity suggests anything falling into black holes, including information, is lost forever. This leads to what physicists call the black hole information paradox, a clash between quantum mechanics rules and general relativity predictions. Strange quantum particle behavior like entanglement and tunneling also defies classical space-time understanding. With entangled particles, they can influence each other instantly, regardless of separation distance. This seems to violate relativity's basic principle that nothing can travel faster than light speed. In relativity, locality ideas are fundamental. Objects in one location can't influence objects in another location unless signals or forces travel between them, and those signals can't exceed light speed. But quantum mechanics doesn't hold this principle. Entangled particles behave as if they're part of the same system regardless of spatial separation. In quantum mechanics, time also doesn't flow smoothly and continuously as we experience daily. Instead, at the smallest scales, time seems to behave more like discrete moment series. Some physicists believe that at quantum levels, time itself might be quantized, meaning it comes in tiny indivisible units, much like quantum mechanics energy. This differs greatly from relativity views, where time is a continuous dimension flowing smoothly like a river. Physicists have been trying to resolve this tension between quantum mechanics and relativity for decades. So far, complete theories uniting the two have remained elusive. One leading candidate is string theory, suggesting all universe particles and forces are made of tiny vibrating strings. In string theory, space and time aren't fundamental. They emerge from these string vibrations at deeper levels. Another approach is loop quantum gravity, suggesting space and time are made of tiny loops, and that at quantum levels, space-time fabric is granular, not smooth. If space and time aren't fundamental, but instead emerge from the quantum world, then our experienced universe is only one layer of much more complex reality. The classical, predictable space-time world is built atop chaotic, uncertain quantum worlds where usual cause and effect, space, distance, and time rules break down. The 2022 Nobel winners, proving reality's strangeness. In 2022, the Nobel Prize in Physics was awarded to three scientists, Alain Aspect, John Clauser, and Anton Zeilinger, whose experiments were instrumental in proving Bell inequality violations. The experiments conducted by Clauser, Aspect, and Zeilinger did more than confirm quantum mechanics' strange predictions. They fundamentally changed universe understanding by proving Bell inequality violations, showed that classical ideas of local, objective reality, where objects have definite properties and only influence each other through local interactions, is not how the universe works. Their experiments confirmed quantum mechanics' strange predictions, while hinting at deeper, unresolved questions about reality's nature. If space and time aren't as fundamental as once thought, what lies beyond them? How do we reconcile smooth, continuous space-time fabric in general relativity with strange, non-local particle behavior in quantum mechanics? These are questions physicists still grapple with today, and Clauser, Aspect, and Zeilinger's work has provided crucial clues for exploring these mysteries. The 2022 Nobel Prize in Physics recognizes not just these three scientists' achievements, but also the broader shift in universe understanding their work represents. Quantum mechanics has always been strange and counterintuitive theory, challenging basic reality assumptions. But the experiments conducted by Clauser, Aspect, and Zeilinger showed this strangeness wasn't just theoretical curiosity, but fundamental universal feature. John Clauser's work, Unveiling a Quantum World Without Hidden Variables. John Clauser's 1970 seconds work represented a turning point in quantum mechanics experimental verification. When quantum theory's strange predictions still met skepticism, Clauser's experiments offered some of the first direct evidence that the universe might indeed operate in ways defying classical spacetime and causality notions. Clauser managed to bring abstract ideas into laboratories, conducting experiments that could confirm or refute quantum theory's core predictions. At this debate's heart was local hidden variable ideas. In classical physics, it was generally assumed objects had definite properties: position, momentum, energy, whether measured or not. This idea is often called realism, the belief that physical worlds exist independently of observation. When quantum mechanics emerged in the early 20th century, it challenged this assumption by suggesting at microscopic levels, particles could exist in state superpositions. They could be in multiple places or have multiple properties simultaneously, and only when observed would they collapse into one state. This deeply unsettled many physicists, including Albert Einstein, who famously argued that God does not play dice with the universe. Einstein believed there must be hidden variables, factors we couldn't see or measure, that determined quantum particles' seemingly random behavior. Bell's theorem, proposed in 1964, offered ways to test hidden variable ideas. Bell formulated mathematical inequalities, now known as Bell inequalities, which provided methods to determine whether hidden variables could be at work. Clauser took up the challenge of testing Bell inequalities in laboratories. Working with Stuart Friedman, Clauser set up experiments where entangled photon pairs were emitted from single sources and sent in opposite directions to two detectors. According to quantum mechanics, if two photons were entangled, measuring one photon's state would instantly determine the other photon's state, regardless of separation distance. In classical physics, this would seem impossible. No signals could travel faster than light speed. So how could particles light years apart influence each other instantaneously? Clauser's experiment was among the first to directly test this prediction by measuring two photon polarizations and comparing results. Clauser and Friedman could calculate whether outcomes violated Bell inequalities. Results demonstrated photons did violate Bell inequalities. This meant entangled photon behavior couldn't be explained by any local hidden variables. No classical mechanism could account for correlations between the two particles. Instead, results pointed to conclusions that quantum mechanics was correct and entanglement was real. Clauser's work provided experimental evidence for something previously dismissed as mathematical curiosity. Quantum entanglement, which Einstein referred to as spooky action at a distance, wasn't just theoretical oddity, it was real phenomena that could be measured and tested. His experiments also had broader implications for reality's nature itself. If there were no hidden variables, then quantum particle behavior wasn't determined by underlying classical laws. Instead, measurement outcomes were genuinely random, governed only by quantum mechanics probabilities. This led to profound shifts in how physicists understood universal nature. In classical physics, the universe was seen as a deterministic system, where past determined present and present determined future. But in quantum worlds, randomness and uncertainty were fundamental reality aspects. Moreover, Clauser's work raised important questions about observers' roles in quantum mechanics. In classical views, measurements simply revealed pre-existing object properties. But in quantum worlds, observation played more active roles. According to theory, measurement acts caused wave function collapse, bringing particles into definite states. This suggested reality, at least at quantum levels, wasn't something existing independently of observation. Instead, observers played crucial roles in shaping measurement outcomes. Alain Aspect's experiments, closing loopholes in Bell tests. Alain Aspect's 1,980 seconds experiments further strengthened the case for quantum non-locality. His work wasn't just about replicating previous Bell theorem tests. It was about refining those tests to eliminate potential loopholes and doubts. By doing this, Aspect and his team helped cement ideas that entangled particle behavior wasn't something explainable by hidden variables or faster-than-light particle communication. Earlier experiments like Clauser's had already provided strong quantum mechanics evidence. However, Clauser's results left open some possibilities for skeptics to argue hidden factors might still influence experiment outcomes. These were referred to as test loopholes. One major loophole Alain Aspect addressed in his experiments was the locality loophole. In Clauser's experiment, detectors used to measure entangled particle properties were set before particle emission. This raised questions whether particles somehow knew detector settings, allowing them to coordinate behavior, mimicking quantum entanglement effects. If particles could exchange information during experiments, even at faster-than-light speeds, this would suggest results weren't purely quantum mechanics consequences, but could be explained by hidden particle communication. Aspect's experiment dealt with this problem by taking crucial steps to alter detector settings while particles were in flight. Instead of setting detector parameters in advance, Aspect introduced random elements into experiments by changing settings only after particles had been emitted and were on their way to detectors. This eliminated possibilities that particles could have known settings in advance, thus closing locality loopholes. His results showed that even with randomized detector settings, particles continued violating Bell inequalities, providing strong evidence quantum mechanics was correct, and no local hidden variables or faster-than-light communication was at play. Aspect's work's technical achievement was significant. Changing detector settings mid-flight was no small feat. It required precision timing and advanced technology. Particles, often photons or light particles, travel at incredibly high speeds, altering detector settings in brief moments, while particles move between sources and detectors, required synchronization levels never before attempted in such experiments. Yet Aspect's team successfully implemented this change, proving experimental design was sound and reducing chances any hidden communication could explain results. With locality loopholes effectively sealed, it became much harder for skeptics to argue experiment results could be explained by classical physics or undiscovered forces. But Aspect's work didn't stop there. He also tackled another significant problem in these experiment types: the detection loophole. This loophole arises when not all measured particles are detected during experiments. In earlier tests, detectors didn't always catch every photon, and some particles would escape without measurement. This left open possibilities that detected particles behaved in ways violating Bell inequalities, while undetected ones might have followed classical physics rules. If this were the case, it would suggest results were biased by only measuring certain particles. Thus, Aspect also improved his detector efficiency to reduce undetected particle numbers. By ensuring higher photon percentages were actually measured, Aspect's experiments made it less likely results were skewed by only measuring certain particles. As with locality loopholes, results still showed Bell inequality violations, suggesting quantum non-locality was indeed a fundamental universal feature. The more loopholes that were closed, the stronger quantum mechanics evidence became, and the more classical universe understanding was challenged. By addressing loopholes that cast doubt on previous experiments, Aspect's work provided much firmer foundation for ideas that quantum entanglement was real and the universe didn't operate according to classical local rules. Anton Zeilinger and quantum teleportation, probing reality's edge. The experiments conducted by Clauser and Aspect provided definitive quantum entanglement proof, confirming particles' strange non-local behavior. Building on this solid foundation, Anton Zeilinger took the next logical step. He asked, if particles could be entangled and share information instantaneously, could this principle be used to teleport information from one particle to another without direct physical contact? The answer was yes, and this concept became known as quantum teleportation. While classical sense teleportation, instantaneous object movement, remained science fiction, what Zeilinger accomplished was profound in different ways. He and his team demonstrated ability to transfer particle quantum states from one location to another, using entanglement as transfer conduit. This was no small feat and required intricate setups involving lasers, photons, and measuring devices capable of detecting quantum states with great precision. Zeilinger's experiments often involved entangling photons, light particles, as they're easier to manipulate than heavier particles. In typical quantum teleportation experiments, 3 particles are involved: 2 entangled particles A and B, and a third particle C, whose state is to be teleported. First, particle C interacts with particle A, causing A's state to change. Because A is entangled with B, this interaction causes B to take on states related to C's state, even though C and B never interacted directly. This way, quantum information about particle C is transferred to particle B, effectively teleporting C's quantum state. What's critical to understand is that particle C's physical matter doesn't move, only information about its quantum state does. This makes quantum teleportation different from movie and book teleportation. In quantum teleportation, it's not about moving objects from one place to another, but about transferring information that defines object quantum properties. This might seem abstract, but it has profound implications for universe understanding. Zeilinger's work showed that at quantum levels, information might be more fundamental than particles themselves. Zeilinger's experiments also built on the no-cloning theorem concept, a quantum mechanics rule, stating it's impossible to make exact copies of arbitrary, unknown quantum states. Quantum teleportation doesn't violate this rule, because original states, in a sense, cease to exist in original forms once teleported. This subtle but crucial detail underscores how deeply quantum mechanics diverges from classical intuition. In classical physics, copying information or objects is straightforward, but in quantum worlds, rules are entirely different. Zeilinger's teleportation experiments played within these strange quantum laws, demonstrating that even though we can't make perfect quantum state copies, we can still transmit them across space instantaneously, using entanglement. In one later experiment conducted in 2012, Zeilinger and his team successfully teleported photon quantum states over distances of over 143 kilometers between 2 Canary Islands. This experiment was groundbreaking because it showed quantum teleportation wasn't just theoretical possibility. It could be done practically over significant distances. The experiment also reinforced ideas that entanglement is real and robust, even when entangled particles are separated by large distances. This result was an important step toward future technologies like quantum communication and quantum networks, which could revolutionize information transmission, making it far faster and more secure than traditional methods. His experiments showed information could be transferred in fundamentally different ways than anything we experience in macroscopic worlds. It raised possibilities that information, rather than being just physical system properties, might be something even more fundamental. In fact, some physicists began speculating, Information might be the universe's most basic building block, more fundamental than particles or energy. According to this view, reality itself could be seen as vast information webs, with physical objects and particles merely being underlying structure manifestations. Understanding Bell inequality violations. Bell inequality violations stand as one of modern physics' most profound results. It forces us to rethink universe understanding, raising questions about reality's very nature. In experiments testing Bell's theorem, when measurements were made on entangled particles, results showed correlation levels that couldn't be explained by any local hidden variable theory. The only conclusion was that either locality, the idea that objects are only affected by nearby environments, was wrong, or the universe works in ways stranger than we can imagine. One way to think about Bell inequality violations is comparing them to flipping two coins. If you flip two physically separate coins, their outcomes should be independent. Sometimes both coins will land heads, sometimes both tails, and sometimes one heads and one tails. Over time, you'd expect to see certain outcome distributions. But imagine situations where every time you flipped one coin, the other coin instantly reflected the same result, regardless of separation distance. This would suggest the two coins are somehow connected in ways defying classical physics laws. This is similar to what physicists found when measuring entangled particle behavior. Outcomes were more correlated than they should have been if each particle was acting independently based on local information. Bell inequality violations don't just challenge locality ideas, they support ideas that reality at its most fundamental levels may not be made of solid, stable objects, but rather of probabilities and particle relationships. These particles only seem to choose their states when observed, and until that moment, their properties remain in limbo kinds. This leads to one of Bell inequality violations' most unsettling implications. The universe may not be as real as we think. If particles don't have definite properties until observed, then what is the universe like when no one is looking? Does the moon exist when no one is observing it? Or does it only snap into existence when measured? These questions, which might seem like philosophy stuff, are raised by real experimental data. Bell inequality violations force us to confront possibilities that observation acts are not just passive information-gathering processes, but active processes helping create reality itself. At these ideas' hearts is non-locality concepts. In classical physics, events happening in one place can't instantly affect distant things. This idea is rooted in notions that nothing can travel faster than light speed, as Einstein's relativity theory tells us. But Bell inequality violations suggest that at quantum levels, this limit doesn't hold. Entangled particles seem to communicate with each other instantaneously, regardless of distance between them. This isn't communication in classical senses. No signals are sent from one particle to another, but correlations between two particle states are undeniable and happen faster than light could travel between them. This is what physicists mean when they say quantum mechanics is non-local. Events in one place can have instantaneous effects in another, without physical connections between the two. Is the universe non-local, or does it not exist? Bell inequality violations present us with two potential ways to understand reality's nature, both challenging everyday experiences and classical physics foundations. Either the universe is deeply non-local, meaning events in one place can instantaneously affect distant events, or the universe doesn't exist as we think it does. Both options seem to stretch limits of what we find intuitively acceptable, but they are inevitable conclusions drawn from decades of quantum mechanics experimental results. If we take non-locality ideas seriously, then the universe is connected in ways defying classical understanding. This means space-time fabric, which seems so solid and orderly on human scales, might not apply at quantum levels. Instead of objects separated by distances and moving through time linearly, quantum mechanics suggests particles can be linked across vast distances, interacting as if space between them doesn't matter. Non-locality implies information or influence can be shared between particles faster than light speed. In classical physics, Einstein's relativity theory sets absolute speed limits light speed in vacuum. Nothing is supposed to exceed this limit. But quantum entanglement doesn't follow this rule. This doesn't mean information is transmitted faster than light, at least not in ways we can harness or observe directly. But it does mean our intuitive space-time views don't fully apply at quantum levels. One possible interpretation is that the universe is interconnected on fundamental levels in ways we don't yet understand. Perhaps space and time are not basic building blocks of reality, but emergent properties arising from something deeper. In this view, the universe is not made of individual objects moving through space, but of relationships and interactions between particles. And these relationships extend across what we think of as distances. This would mean locality. The idea that objects only affect immediate surroundings simply doesn't apply at quantum levels. Another way to think about non-locality is imagining space itself is an illusion, or at least not fundamental. What we perceive as distance might be more like side effects of how our brains interpret information rather than true universe properties. In this interpretation, the reasons particles can be correlated at distances are that at fundamental levels, they are not actually separated by space at all. Space is something emerging from underlying quantum reality, but it doesn't exist as we usually think of it. The other, perhaps even more unsettling possibility, is that the universe doesn't exist as we traditionally understand it. Quantum mechanics has led some physicists and philosophers to question whether reality is objective or whether it depends on observation. In classical physics, we assume objects have definite properties, but quantum mechanics suggests particles don't have definite properties until measured. Until particle states are observed, they exist in limbo kinds, superpositions of all possible states. If particles don't have definite properties until observed, then does the universe exist the same way when no one is looking? This idea, sometimes referred to as observer-dependent reality, suggests observation acts might be necessary for the universe to take on definite properties. In this view, reality is not something existing independently of us, but something co-created through observation processes. This doesn't necessarily mean the universe ceases to exist when we aren't looking, but it does challenge classical ideas that the universe is objective, stable things existing independently of us. Instead, it suggests reality might be more fluid and dependent on interactions between particles and possibly observers than we ever imagined. Some quantum mechanics interpretations, like the Copenhagen interpretation, lean toward this view, suggesting particles don't choose definite states until observed, and until that moment, reality remains indeterminate. There are other quantum mechanics interpretations trying to avoid observer-dependent reality ideas, but none fully resolve paradoxes raised by quantum entanglement and non-locality. For example, the many worlds interpretation suggests all possible quantum measurement outcomes actually occur, but in separate parallel universes. In this view, when we observe particles, we aren't causing them to choose states, but instead finding ourselves in one of many possible realities. Each time quantum events occur, the universe splits into multiple branches, each corresponding to different outcomes. The many worlds interpretation avoids observer-dependent reality problems, but at the cost of introducing infinite numbers of parallel universes. It suggests our experienced universe is just one of many, and all possible realities exist simultaneously. While this might seem like strange ideas, it is one way to reconcile quantum mechanics' weirdness with classical objective reality.